Hello, the topic for this video is Introduction to Free Space Optics. Free Space Optical Communication, FSO, is an optical communication technology that uses light propagating in free space to wirelessly transmit data for telecommunications or computer networking. Free space means air, outer space, vacuum, or something similar. This contrasts with using solids such as optical fiber cable or an optical transmission line. The technology is useful where the physical connections are impractical due to high costs or other considerations. For design and simulation, the fundamental elements that form an FSO system are the FSO transmitter, an FSO channel and the FSO receiver. Here TX and RX represent transmitter and receiver respectively. The transmitter includes the PRBS, pseudo-random bit sequence, generator, NRZ pulse generator, a laser source and MZM, Mach-Zehnder modulator. In the simulation shown, data generated by the PRBS generator at a data rate of 10 Gbps is encoded and light modulated using MZM, where laser source acts as the carrier source with wavelength 1550 nanometers and power 20 dBm. This modulated light is amplified using optical amplifiers before transmission to a range of 40 km. The gain of the amplifier is set as 20 decibels. The amplified signal is then directly sent to the receiver through a free space optical channel. Actually, free space optical channel is a subsystem of two telescopes with FSO channel between them. The apertures of transmitter and receiver are set to 5 cm and 20 cm. The beam divergence is 2 mrad. In practical cases, there is attenuation in the received signal due to atmospheric conditions of the channel. It is possible to set the attenuation losses in the FSO. Typical attenuation values of 3 conditions: clear, haze and fog are 0.43 dB/km, 4.3 dB/km and 43 dB/km respectively. Initially, the attenuation value is set as 0.43 dB/km, clear. The optical signals from the FSO channel are received by photodetector pin. A low-pass special filter is used to filter the signal from noise. This simulation uses 3 visualizers, namely optical power meter, optical spectrum analyzer, and Burr analyzer. Optical spectrum analyzers provide the facility to analyze the optical spectrum. Optical power meters gives the power received in both dBm and watts. Burr analyzer automatically calculates the Burr value, Q factor and display eye diagram. For result and discussion, the system is analyzed under a clear condition with an input power of 20 dBm, the bitrate of 10 Gbps, and at a range of 40 km. The eye diagrams of this system under clear conditions are as shown in this video. This system exhibits a better Q factor and low Burr under these atmospheric conditions. The attenuation effects from these disturbances can be minimized by the co-FDM modulation with polarization. The most important challenge faced by this FSO system is fog. Its attenuation is taken as 43 dB/km. In FSO system under fog with the same other conditions, it is seen that the Q factor of single TX-RX FSO system is decreasing, which can be improved with 4TX/4RX FSO system. For the conclusion, free space optics is a promising communication technology in the near future. Due to the atmospheric disturbances, there is a distortion of signals at the receiver. But by using new techniques, it is possible to reduce the atmospheric effects on the optical signal. Use of spatial diversity and co-FDM with dual polarization in the FSO system increased the efficiency of systems under different disturbances. Even though the Q factor of the FSO system decreases on increasing attenuation, the 4TX/4RX shows a higher Q factor, so better performances. Similarly, Co-OFDM system with dual polarization reduces the attenuation effects on the optical signals propagating through the atmosphere. That's all for this video. Thank you for watching and have a good day. Bye bye.